We're very happy to have here today uh, Gautam Satishchandran, who is a PhD student at the University of Chicago in the United States of America under the supervision of Professor Robert Manuel Wald. And today, Gautam is going to talk about infrared finite scattering theory in QED and quantum gravity. So, Gautam, the stage is yours.
Okay, yes, so thank you for the invitation to speak. It's really an honor to give a talk. I've never visited Belém, but maybe sometime in the future. Okay, so as was just stated, I'll be talking about, well, my title, which is Infrared Finite Scattering Theory in QED Quantum Gravity. And this is the kind of technical title. The question really that I'll be addressing is how does one do scattering theory in QED and quantum gravity, which may already be a puzzle to you. You know, there are many books that are written about scattering theory in QED, and maybe there's some people do scattering theory in quantum gravity, but hopefully by the end of this talk, you'll see that there's still some really, there are some major open questions, and we really try to address these questions, in particular in the infrared sector, in both of these theories. So this is work I did with, well, some of the preliminary ideas that I'll be talking about can be found in this paper that I highlighted here. This paper dealt with many other topics besides scattering theory. We did present some of these ideas, and in this paper that should appear shortly with Kartik Prabhu at UCSB, we really fleshed a lot of the details about what I'll be telling you about today. Oh, and I can't see your faces, unfortunately, so just feel free to interrupt at any time if you have any questions. Okay, so just a brief roadmap for this talk. Well, first I'll mostly be focusing on classical gravity and quantum gravity, since this is a gravity meeting, but we'll be looking at QED to get some insights. So first we'll be looking at classical gravity, and I'll be explaining what gravitational radiation is, or the kind of modern understanding of gravitational radiation, and a particular observable known as the memory effect, which is going to play a central role to our discussion. And in particular, we'll be using a useful formula of the decomposition of the memory in terms of what's known as charge fluxes. So if these words don't make sense to you, I'll explain them quite shortly. So after we get this necessary ingredients, we can then turn to the quantum theory. And the kind of key thing that we'll be doing in this talk to basically solve this problem that I'll be posing of how to do scattering theory is to really delineate what it means to specify a quantum theory. In particular, we'll be taking the so-called algebraic approach, which really makes it clear what is necessary to specify quantum theory, in particular quantum gravity. And then we will see from this intrinsic structure how the infrared problems of all quantum field theories, and in particular quantum gravity, appear. Okay, so that's a tall order, and then what we'll be doing is studying what are the so-called scattering representations? What are the Hilbert spaces that one needs to study scattering theory? And we'll see a distinguished class of states, in particular in the context of QED, and then we'll try to lift this result in QED to massless QED, linearized quantum gravity, and then full quantum gravity. What we'll basically see is that there's a primary to doing so in all theories except QED. So there's a QED is kind of a fluke in this regard, as opposed to a thing to follow. Okay, so if these words did not really make sense to you, we'll be taking them step by step. And in the end, we'll basically summarize what is the status of scattering theory in all of these contexts. Okay, so just a bit of background. Well, these infrared divergences, if you open up, for example, Peskin and Schroeder or Weinberg and so on, are a ubiquitous feature of quantum field theory. And as we'll see in quantum gravity, and later in this talk, we'll make an explicit link between these IR divergences and a physical observable of gravitational radiation, in particular, the memory effect. So the standard approach to dealing with infrared divergences, again, if you all open up these very old books, is to forego defining the concept of an S matrix or defining the concept of an out state and compute only what's so-called inclusive cross-sections, where you kind of put in an infrared cutoff, and then integrate out all the low frequency degrees of freedom. So this is perfectly well defined to a large degree, and gives a nice calculation of what people will see in the LHC example. However, this approach fails to define what the out state really is. As we'll see, that's going to be the primary approach that we'll be trying to take, is really defining what the out state really is. And so one cannot ask any more subtle questions besides which one gets from these inclusive cross sections. In particular, if you want to ask about entanglement decoherence due to low frequency radiation, or information loss or recovery of a state due to some process. In particular, of course, I'm thinking of black hole evaporation or something, which has been argued by a number of authors. This information could be hiding at low frequencies. These questions cannot even be addressed with the current methods of calculation, and in particular, really because the S matrix is really not defined when you include low energy degrees of freedom. Okay, so in the talk, the two kind of things that we'll be doing in this talk is, well, one, we'll be providing a new perspective of this problem. This problem is quite old. It's been around since the 1930s. And the idea is that we'll be defining the kind of asymptotic quantum theory without an a priori choice of a Hilbert space. Okay, so that's the kind of main tool that we'll be using. This allows us to basically consider all representations at once, the different Hilbert space representations, and identify a privileged class of representations, and particularly these so-called Coolidge-Fadeev representations in massive QED, which do map to each other under scattering. And then we will prove that such representations are not physically reasonable representations. They don't encode physically reasonable states in all other theories except for in massive QED. So QED is kind of a fluke in this regard. Okay, so let's get started, and let's first just focus on classical gravity. And in classical gravity, the effect that I've been telling you about or alluding to is the memory effect, which is the permanent relative separation of an array of test particles brought about by the passage of a burst of radiation. So if I allow some radiation to pass through your screen, through these ring of test masses, they will oscillate and settle down at late times to positions that are permanently displaced relative to their original positions. And that is an instance of the gravitational memory effect. Okay, so a bit more quantitatively, the memory is a property of gravitational radiation, and in particular, we'll be studying radiating spacetimes in asymptotically flat spacetimes. So the metric tends to the Minkowski metric plus order 1 for R currents, where R is this null direction moving off in this way, off of some flash of the light bulb that I've given here. So it's very useful to draw this surface here, which is, asymptotically is roughly what one means by null infinity. It's the infinity that null, radiation gets out to. And what we'll basically be doing is working on this kind of surface to encode, gravitational and radiating degrees of freedom. So U is the retarded time moving up and down the surface, and the flashes of the light bulb encode basically topological two spheres that intersect this cone. So these circles here are really two spheres because I've reduced one dimension. So these are the coordinates that we'll be using. These U and theta are coordinates on this kind of light cone-like object at large distances. Okay, and then so I basically gave you what's known as null infinity. You can completely compactify the space-time and bring all the infinities to kind of a finite place. This is known as the Penrose compactification, where null infinity is given here. This is where the radiation gets out to. I plus and I minus are where massive particles, end and begin. So massive particles start here and end here. I0 is spatial infinity, which is basically where, if I go off in spatial directions, this is the infinity that spatial directions reach. And if I'm looking at, for example, the merger of some two stars or something like that, so they come in from past time like infinity, and they merge, and here's the event in which they merge, a burst of radiation is reached, and you can imagine a LIGO detector out here, getting that burst of radiation, and then a final object goes out to future time infinity. Okay, and so now quantitatively encode the radiation. Well, the radiation is encoded in the news tensor, which is basically the time derivative of a metric component. So this is the shear, which it basically encodes the metric degrees of freedom, the transverse trace degrees of freedom, where capital indices are tensors on the sphere, and you take its U derivative and you get this thing known as the Bondi news tensor. So this encodes the radiative degrees of freedom. And the memory tensor is, we define as the integral of the news tensor over retarded time. So why is this called the memory tensor? Well, if you just calculate the relative displacements that I was showing you before of two nearby test masses due to some gravitational radiation, well, the change in the relative displacement, how you calculate that is you take the initial displacement of the test masses, they map from the initial displacement to the change in the final displacement at leading order 1 over r, so at large distances, is this exact memory tensor. So in this sense, the memory tensor encodes the memory effect. Okay, are there any questions so far? Okay.
Please go ahead, Gautam.
Yeah. So, and if you're curious, if you're looking at a LIGO signal, for example, you would see if there was non-vanishing memory effect, is that you would see a final offset in the signal between early and late time. So there would be some value of the signal at early time, and this is some gravitational wave, and then at late times you get this final offset, and the value of the difference between the metric at early and late times is the memory. And a different value depending on where you are on the asymptotic sphere. Okay, so that's what the memory effect is, but there's a very useful formula that we'll be kind of using for the rest of this talk, so I'll unpack it a bit slowly. The memory, using Einstein's equation, satisfies this equality, where it can be written as the sum of 3 terms. So the first 2 terms are known as the so-called ordinary memory effect, which are the difference of what's known as, in the nomenclature, super translation charges. So are these super translation charges? Well, it's the difference at early and late times where, I'll go back, the gravitational radiation at early and late times is tending to 0. It's, it's turning off at asymptotically early late times. So when the gravitational radiation is dying off, these charges basically correspond to the mass multipoles of the space-time. So what do I mean? Well, for a massive body in stationary space-time, these charges with some outgoing momentum given here, these charges basically encode all of the mass multipoles of the space-time. So the spherically symmetric part of this equation is just the total mass, and then higher multipoles of all of the mass, of boosted mass is encoded by this formula here, where gamma here and this denominator are the usual kind of boost factors one gets. For when you kind of boost a stationary body. Okay, so that's what these super translation charges are. They're just mass multipoles. So if you have a change in the mass multipole, from early to late times, like quadrupole to monopole or something like that, you'll get a difference of charges. Okay, and the flux of gravitational energy is this term here, this last term, which is the integral of the nu squared along scribe. So this basically encodes the total flux of gravitational radiation energy at each angle on the sphere. And that's so therefore, add these quantities together and you get the 2 derivatives of the memory effect. These derivatives on the sphere. Okay, so now this is the picture I want to give you, which is if I have some incoming data, which is some incoming radiation, and some incoming momenta of some massive bodies, well, the charge at time like infinity is just simply the sum of these 2 charges that I gave you before, these formulas that I gave you before, so they just linearly add. And the charge and the incoming radiation has a potential incoming memory, that's possible, and an incoming flux of energy. So the incoming data determines this term, and determines the flux of energy, and therefore by this formula, the charge at spatial infinity, all the mass multipoles, are determined. Okay, and one can analogously do this for the outgoing stuff. The outgoing memory has, and the outgoing charge is determined by the outgoing mass of body, and the outgoing flux of energy is determined by the outgoing energy, outgoing radiation. And the reason why I don't distinguish between the charge at spatial infinity coming from the top of this diagram and the charge at spatial infinity coming from the bottom of this diagram is because these charges match. So this charge is in the sense conserved, in the sense that if I take the limit from past nullity and the limit from future nullity, this charge is conserved. So this is the whole picture. Basically, incoming data and outgoing data are constrained by this charge matching, and this is in some sense known as an infinite number of conservation laws, because of you get one for every angle, YLM, every angle on the sphere. Okay, so now with this kind of classical structure in mind, we can turn to what how does one do scattering in quantum gravity? Well, okay, you should already be skeptical, because even in the absence of theory of quantum gravity, so what do I mean by theory of quantum gravity? Well, even if we don't have a theory of quantum gravity, the asymptotic theory can be straightforwardly defined. And so how do I do that? Well, the standard presentations, so this is the major departure from, or major kind of deviation from, how we view this problem of scattering theory. So in the standard presentations of quantum theory, one thinks of observables as being defined on a Hilbert space. So, however, the central question of this work shall be whether there exists a preferred Hilbert space for scattering of asymptotic states. So it is therefore problematical to fix from the outset a particular Hilbert space. And in particular, we shall show that such a preferred Hilbert space generically doesn't exist except for in certain special cases, and we'll enumerate those cases. So really, it's really problematical to define Hilbert space of states first. It's much more natural to define in the following way. So a quantum theory is defined by an algebra of observables. So what I mean by that? Well, it's a collection of operators together with their commutation relations. This is kind of loosely speaking, but essentially correct. So for example, if I want to characterize the out algebra, I would write down the news operator, the charge at spatial infinity, and the outgoing flux of energy, as well as the identity operator. And then I would basically write down commutation relations between these guys such that the algebra is closed. And so I won't go through the actual, one can derive the commutation relations of the news operators. And this is not going to be important for the talk, but you can see that it's a derivative of a delta function in retarded time and a delta function in angles. And these metrics on the two sphere, these Q's are, this combination just ensures that the news is trace-free on both of these pairs of indices. Okay, so but it's not going to be essential that you remember or memorize these lists of commutation relations. The important point is that it forms a closed algebra. And the other essential point is that one finds is that the charge at spatial infinity and the outgoing flux satisfy the same commutation relations. They both generate a time derivative of the news at each angle on the sphere. So in some sense, what really this is doing is called, the charge at spatial infinity generates time translations at each angle. So if that doesn't, don't worry about it. The clear point is that this algebra is closed and the action of the charge is identical to the action of the outgoing flux. And the charge at time like infinity vanishes because we're going to fix to vacuum quantum gravity in this. I mean, vacuum quantum gravity is hard enough to talk about, so we'll just stick to that. Okay. Again, yeah, feel free to interrupt at any time if you have any questions. Okay, so now I want to just give you the picture again, the simple picture. So in algebra and the out algebra are basically generated by these operators that I gave here. So the news, the outgoing flux, and the charge, and the in algebra is then again the news, incoming flux, and the charge at spatial infinity. Okay, so what's happening with the memory? Well, the memory satisfies this formula, if you recall. It has this flux term and this charge at spatial infinity. The charge at time-like infinity is 0. Well, recall that the action of the flux and the action of the charge at spatial infinity had this, the same action on the algebra. The commutation relations are the same, which means that their difference implies that the memory commutes with all observables in the algebra. So this is a key point, that the memory is a central element of our out algebra. And it commutes with all observables in the algebra, and we'll be using that later. So that's an important point. Similarly, one finds that the in-memory also commutes with all observables in the algebra. Okay, so this basically defines what we mean by the observables that we're interested in: the news, the outgoing flux, the charge, and this combination gives also the memory. Okay, so if I give you the operators, that's not sufficient to define the quantum theory, to tell you how to define states. And this is also a significant departure from the kind of textbook approach, but this is essential, I would claim, for understanding these infrared properties, or quantum theory in general. So the out algebraic state is mapped from the out algebra. We define as a map from the out algebra to a collection of correlation functions. So, for example, they should say out, not algebraic state. So, like, let's look at this states. We'll call it psi out, which is take the out algebra and specifies a list of correlation functions. So, it's defined by basically specifying a list of endpoint correlation functions, which are these. For example, I've written out these news operators here. So if I give you all correlation functions on the news, then I've defined what the out state, the state is in terms of all these news operators. Okay. So I basically have to give you a list of functions, endpoint functions on Scry. And the key point is that psi is not a vector in a Hilbert space. I've defined what I mean by a state without choosing a representation. However, you can always represent psi as an element of a Hilbert space whose correlation functions are given by these relations. However, it is not necessary to make this choice in the algebraic formulation of the theory. And that is essential. Okay, so this is not enough. I could write down arbitrary functions, you can imagine, that are not physically reasonable. So you need to put a physical reasonable requirement on these functions. And a physically reasonable state in our context is whose correlation functions are locally equivalent to the free field correlation function. So this amounts to requiring that the singular structure of the correlation functions are equivalent to that of the vacuum state, the out vacuum. So for example, point function of the out vacuum looks like this, where it has a delta function and angles again, and it has the singular behavior in U1 and U2. Again, these metric, these two-sphere metric combinations are just making sure that it's trace-free on this pair of indices, on these two pairs of indices. Okay, so this again is not important as a particular structure, but the point is that the singular structure kind of determines what we mean by a physically reasonable state. And so what do I mean by that? Well, again, I prefer a picture over words. So so I now define a theory, I give you the out algebra, but then I give you, to define a state, I give you a list of correlation functions, in this particular case, focusing on the news, where the difference of the correlation functions with the vacuum correlation function is a smooth function. So as long as that is true, then I'm calling that a well-defined and for the 1-point function is smooth. The 2-point function difference with the vacuum is again smooth. The 3-point function difference with the 3-point vacuum function vacuum is smooth, and so on and so forth. And you do the same thing for the in states. And the thing I'm trying to stress here is that this defines what I mean by the quantum theory. This defines all the physically reasonable in states and all the physically reasonable out states without ever choosing a Hilbert space. Okay, and then how do I encode charge conservation? Well, I basically require that the endpoint correlation functions of the charge in the in state match to the endpoint correlation functions of the charge in the out state. And this is what we mean by conserved. Okay, so now to reiterate or beat a dead horse again. So the specification of an algebra of operators as well as a class of reasonable algebraic states is completely sufficient to specify a quantum theory. Okay. However, the current formulations of scattering theory require, if you open up Peskin and Schroeder again, as an example, require additional structure of specifying an in and out Hilbert space. So that's a that's a specific specification of a Hilbert space of states, and then one defines an S matrix as a map between in and out Hilbert spaces. So note, as we'll see, these states, the states that satisfy these conditions, do not form a Hilbert space necessarily. A Hilbert space is a stronger condition than just requiring these conditions. And we will see this explicitly. Okay, so one then requires that the in states map to the out states by this S matrix, and this defines the S matrix. Okay, so the question is, for the remainder of this talk, does there exist a preferred Hilbert space of in and out states for scattering theory? Well, in quantum gravity, well, but more generally in quantum field theory, if you have any massless fields. Okay, so now the approach that one should first take is really, when you're given an algebra, what are the kind of Fock representations, or what are the Hilbert space representations that you can write down? So in particular, if I'm given this out algebra, what are the Fock representations, the irreducible Fock representations of my algebra? And we'll see, possibly surprisingly, that there are many of them. So how do we quickly enumerate them? Well, we use this fact that the memory commutes with all elements of the algebra, and therefore is a multiple of the identity in every irreducible Fock representation. So it has to be a multiple of the identity. And the standard Fock representation, the standard Fock space with the invariant vacuum, has no radiation in it by definition. So therefore, it must annihilate this state. Well, then, since it's a multiple of the identity, it must annihilate every state in the usual Fock space. And so, surprisingly, all states in the standard Fock space that one uses in scattering in quantum field theory have zero memory. Okay, so memory, recall, is an observable is a detectable observable, and we really would like to consider states with memory. So how does one do that? Well, in the algebraic approach, you just take all the correlation functions and you displace them by a solution with memory. So the 1-point function, instead of vanishing in the vacuum, now corresponds to a classical solution with memory. The 2-point function, again, you take the 2-point function of the vacuum and you displace it by the product of solutions with memory. And you do that with the 3-point function, and so on and so forth. Okay, so this defines an algebraic state, and then you can represent that state as an element of a Fock representation with this vacuum state omega delta, and the elements of this Fock space F delta are eigenstates of the memory operator with eigenvalue delta. So whatever the memory was of this classical solution. So this amounts to basically create a coherent state, if that clarifies anything. Okay, this is cut off a little bit. I'll just explain what I mean here. So and you can show, it's straightforward to see that if you Fourier transform something that has this kind of step function behavior between early and late times, at low frequencies, the Fourier transform of a step function diverges like 1 over the frequency if the memory is non-zero, plus things that are smooth in the frequency. And one can compute the norm of a state with memory, in particular this vacuum state, in the usual Fock space, and this is where the source of all these infrared divergences come from. This state, the norm is infinite, and it is infrared divergent at low frequencies. And what's cut off here is basically the statement that, and I'll just say it in words, this out Fock space F delta is unitarily inequivalent to the usual Fock space. So the space of all irreducible representations of our algebra are, all deltas for all possible memory. So that's an uncountably infinite set of Fock representations that one could possibly scatter out to. And why could one possibly scatter out to it is because the memory is not concerned. We just talked about. So if you can have in states with zero memory and the out state could have memory, an in state with zero memory will scatter to an out state with arbitrary superpositions of memories, and you don't know a priori which superpositions you'll get. So you need to include all of these memory Fock spaces for all possible delta. And a priori therefore unclear whether there exists a physical Hilbert space of asymptotic states which satisfies reasonable conditions. So what is reasonable conditions? Well, one, I'd like the Hilbert space to be separable. Otherwise, kind of the basic calculations of Baskin and Schroeder are really, like scattering amplitudes really are not admissible. So it admits a countable basis. It contains a dense subspace of physically reasonable states, in particular, it has a singular structure, the states. And furthermore, the energy, momentum, and angular momentum of these states are well defined. And finally, well, trivially, we want or non-trivially, but we certainly want this, that the in states in our Hilbert space evolve to out states in our out Hilbert space. That's a clear condition that we would want to have. And I hope it's clear now, this is a highly non-trivial problem, given the fact that we have an infinite number of Fock representations of our outs for the in and the out algebra. So it's not trivial to see which one you want to include for a particular in state. Okay, so now at this point, since I'm roughly halfway through the talk, I should really back up and kind of say that this doesn't arise in quantum gravity, where we don't really have a theory of quantum gravity. It arises in a kind of mundane manifestation, even in QED with the electromagnetic memory effect. This is analogous effect, which is basically given by the integral of the electric field on Scri. And the standard approach is to introduce a cutoff, a frequency cutoff, and only scatter between the zero memory Fock spaces. So if you impose a frequency cutoff here, then you basically don't see this infrared divergence, and the norm of the outstate you can pretend is finite. However, it's infinite as you take the limit of the frequency cutoff to zero. Okay, so one scatters between the usual Fock space, and then you compute inclusive cross sections. So you just integrate out all the low frequency behavior and only ask questions about so-called hard particles, high frequency particles. In this construction, the outstate is undefined, so it's not a very palatable conclusion for a quantum theory. The S matrix is also undefined, and the memory, which is a classical observable, is again undefined. So furthermore, one cannot ask questions about, as I mentioned before, entanglement coherence due to soft radiation. How much information do I lose when I make a measurement, or information loss and recovery with regards to proposals about, for example, the black hole information paradox. So these are all things that cannot be addressed because there is no framework a priori to address them. Okay. However, in QED, there exists a construction of a Hilbert space satisfying items 1 through 3, known as the Fayette dressing. And so this is a central point, and actually appears as a very natural and geometric thing to do from our construction. And so we will see how this arises, and then we'll see if one can implement this in any other theory as well. Okay, so maybe I should stop here and take any questions.
I mean, would you like to stop your presentation now, or just stop to ask if there are questions?
Just to ask if there are questions at all, because this is quite a bit to take in, I think.
Well, I fully agree with you, but I think you should move on to the end, and then we leave questions to the end, because sometimes the questions just they're going to be simple questions and make you digress far back, and something like that. Maybe you just...
Okay, yeah. So let's continue on, and then I can always come back. Okay, so the analogous formula for the memory effect in E&M is memory is a vector on a sphere instead of a tensor on a sphere, and it's the integral of the electric field now. It's the difference of these charge multipoles instead of mass multipoles. So I'll give you formulas in a second. It's a difference between charge multipoles instead of mass multipoles. And note, there's no flux term in massive QED. This is in massive QED. There's no flux term of there's no null memory contribution in massive QED. So it's just a difference in charges. So it's a much simpler formula. Okay. And this is the kind of picture. Well, it looks very similar, but now I've kind of highlighted these orange things. Now you should think of them as kind of electromagnetic degrees of freedom, perhaps they're orange because it's in red. You can use your imagination. So the algebra at Scry is kind of very similar. We have the electric field operator now, as well as this memory operator. And now we have an algebra of operators at time-like infinity, which are generated by the outgoing electron, which is this electron creation and annihilation operators, which are the B dagger and the B, and positron and annihilation operators, which are C dagger and C. Okay, so these are basically create and annihilate outgoing states, or sorry, annihilate outgoing states, the electron of the outgoing electron and positron, and we furthermore have non-trivial charge at time-like infinity now, given by this here, and I put an EM to distinguish from the previous notation. Okay, and we similarly have an in-algebra of operators, which are constructed basically analogously to the out algebra. And furthermore, just as in the gravitational case, charge at spatial infinity is again conserved. So in the context that we had before, the situation is almost identical, except for now we have massive matter. So we have to include stuff at time-like infinities. Okay, so the idea of Fadeev and Coolidge is to, if we want to construct states that map to themselves under evolution, one way and possibly the only way of doing that in this algebra is to reliably do that is to construct eigenstates of the conserved charge. If I construct an eigenstate of the conserved charge, then it should map to an a Hilbert space that's an eigenspace of the conserved charge in the out state. So that's the main idea, is map to itself. We want states that map to themselves under evolution, and we're going to make them eigenstates of the charge at spatial infinities, and the charge is conserved. Okay, so to do this, let's first look at eigenstates of the charge at time-like infinity, and we're looking at in-states, so let's look at the charge at past time-like infinity. The same formula applies in the future, and the eigenstates of the charge are these momentum eigenstates. So these are improper states in the sense that you should really smear them over momenta to get a proper state, but these momentum states are eigenstates, and the eigenvalue is very similar to what we had before, where now Q is the charge of the electron, as opposed to before we had a mass here, and I think we had this denominator was cubed before, but now it's squared. Okay, so the eigenstates of this charge correspond to states where the incoming electron. So in order to construct eigenstates of the charge at spatial infinity, we need to correlate incoming momentum of the electron with electromagnetic degrees of freedom in such a way that we get a definite charge at spatial infinity. So if that's not clear, this picture should be more helpful. If I have an incoming, electron here with some momentum state, some incoming momentum, so that's what's given here, I should tensor in an electromagnetic memory state with memory determined by that momentum. So what I do here, I solve this equation for the incoming memory that I should be attaching, and I solve this equation where the charge at spatial infinity, time-like infinity, is now replaced by the eigenvalue that I gave before, and now I pick a particular charge at spatial infinity. That's the definite charge that I want to stay in. So I start with the state of definite charge, now end up with the state of the same definite charge. So I pick this, and this is determined by the incoming momentum, and I solve for the memory. After solving for the memory, integrate over the diploid of momenta, like as you do in quantum field theory, to get a well-defined state, where F here is just some smearing function, like a wave packet or something. Okay, so this is basically exactly, so this state is an eigenstate of the charge at spatial infinity, and if you wanted to do this with n electrons, you simply sum the eigenvalues. That's all you do, and you do the same calculation. You construct a incoming electromagnetic memory state that satisfies this equation, where you replace this with this sum of eigenvalues. And the corresponding Hilbert space you get from, I gave you the one particle and now the n particle, and you can, create an arbitrary number of particles, and this gives you a Hilbert space, which is all an eigenspace of the charge at spatial infinity with a definite eigenvalue. And they basically correspond to incoming electrons tensored in with non-trivial memory states, electromagnetic memory states, correlated with their momenta. Okay, so an analogous construction yields a out Hilbert space of definite charge, of the same definite charge. And so for each charge at spatial infinity, the resulting Hilbert space is a separable space that maps into itself on evolution. However, there's an important kind of point that I swept under the rug, which is that if the charge is not zero, the incoming and outgoing angular momentum flux of the states are infinite. Okay, so why is that? It's really because the charge at spatial infinity changes under Lorentz boost. So if I Lorentz boost with some velocity parameter v, the charge at spatial infinity changes by the same formula that I gave, or analogous formula as the one I gave you before. So these spaces are not closed under the Lorentz boost and will out of the Hilbert space if I do a Lorentz boost. So the unique Hilbert space that is variant under, that maps itself under boosts is when the total charge at spatial infinity vanishes. Unique in and out Hilbert space, which contains a dense set of physically reasonable states and maps to itself under evolution, is the unique Hilbert space where the definite charge at spatial infinity is set to zero. This includes the total charge, total electric charge, by the way. So you have to, in this construction, you have to send in incoming electrons with positrons, for example, to have a fine scattering. Oh, sorry, with Hilbert space. Okay, so this is known as the Kulish-Faddeev Hilbert space. This is what was proposed by Kulish and Faddeev in the 70s, though not through this kind of more geometric language that I gave you before. And this now just kind of naturally falls out from our construction of the quantum theory. And more recently, Froelich and collaborators, as well as Pavel Duke, have rigorously shown this conservation of the charge and this mapping between in and out Hilbert spaces, in the level of, well, here is in relativistic QED, and this was done in perturbative QED. In both cases, it was rigorously shown that this Hilbert space does map into itself under evolution. Okay, so that's the status of QED, and let me just briefly say what goes on in massless QED as well as in linearized gravity. So in massless QED, the incoming electron is now coming from null infinity. So this actually should be much less curved. It should be 45-degree angle. My apologies. This is now a massless electron coming in from scry minus with some massless momentum. So it's really coming in from past null infinity. And the incoming electromagnetic memory, the incoming state of definite charge is analogously constructed in this way. So you basically take this incoming massless momentum, which is determined by a frequency and an angle coming in from scry. So that's what this p hat is the angle that you're coming in from scry. So is determined by this momentum tensored in with an electromagnetic memory state determined by this incoming momentum, where the electromagnetic memory state is equal to, well, this definite charge that I've fixed at spatial infinity. But now, instead of this other smooth function of angles that we had before, we now have a singular, well, delta function of angles that we have to contend with. Okay, so now the memory is much more singular than it was before. It has to basically is sourced by a delta function in angles, and it's basically straightforward to see that any electromagnetic field with this memory actually has infinite incoming energy and momentum. Basically, the electric field that satisfies this memory effect, that has this kind of angular behavior, if you take the square of that electric field, you're basically, taking the square of something that, whose derivative, it's already quite singular, and then you're squaring it, and you want to integrate that over scry, and you effectively find that that energy is infinite. It's logarithmically divergent in angles. Okay, so I won't go through the detailed calculation of that, but you'll have to kind of trust. So in Massless QED in particular, so that was at the level of classical solutions, but really in the quantum theory as well, if you look at states of definite charge, we can again get finite angular momentum by setting the charge at spatial infinity to 0. So, having positrons come in with electrons and having all the electromagnetic field entering in such a way that all the charges are set to 0. However, we prove that for all states of definite charge, the expected stress tensor of the incoming state is infinite for all such states. Okay, so these are not physically reasonable states. So this construction fails. Now we can turn to linearized quantum gravity, and in linearized gravity with either massive or massless sources, the gravitational field, well, in the massless case, it just barely is smooth enough to yield a finite energy, but it is a finite energy flux. However, in order to have finite angular momentum flux, we need to consider only the states in which all of the mass multipoles vanish. All of this charge at spatial infinity vanish. So if all the mass multipoles vanish, that also means that the total mass vanishes, or the total energy must vanish. And the unique state that has vanishing total energy is the vacuum state. So the only eigenstate of the charge with eigenvalue is really the vacuum state in linearized quantum gravity with massive or massless sources, and therefore the only state that is an eigenstate of the charge with vanishing eigenvalue, the only state that is an eigenstate of the charge is the one that has finite angular momentum is the vacuum state. All the other states that are eigenstates of the charge have infinite angular momentum. So again, does now unreasonable state. So Massless QED and linearized quantum gravity both kind of fail in this regard. Okay, so now what can you do in quantum gravity? So you can't hope that linear quantum gravity is better than linearized gravity. So you cannot hope to have eigenstates well-defined angular momentum if we want to get eigenstates of this charge. However, you can just pose the question. So before, in linearized quantum gravity, one can find eigenstates of the charge at spatial infinity. Just have infinite angular momentum. You could, say, throw up your hands and say, okay, well, let's deal with infinite angular momentum. Maybe if the energy flux itself is finite, then maybe that's enough to just, like we could get away with a little bit, doing scattering theory or something. But the question here we're posing is, do there exist any states besides vacuum which are eigenstates of the charge at spatial infinity? Recall the vacuum has 0 energy flux, so this is 0, and the memory is 0 of the vacuum. So that's definitely an eigenstate of the charge at spatial infinity. Okay, so in QE, the eigenstates correspond to basically correlating the momentum of the electron with the memory of the electromagnetic state. So the analogous question we're asking is, do there exist any states in which the hard, kind of high-frequency gravitons are dressed with low-frequency soft gravitons in such a way to get an eigenstate of the charge at spatial infinity? And we prove kind of the much stronger result, which is that we prove that the only eigenstate of the charge at spatial infinity is the vacuum state in quantum gravity. And so I can give slightly more details on that proof, but this is really the kind of a death to the idea of constructing scattering states that map to themselves under evolution. And this, summarize kind of all of what I've been saying in this kind of theorem, which in massive QED, one can construct a unique Hilbert space of definite spatial infinity charge, which satisfies items 1 through 3. The separable has a dense set of physically reasonable states, and it maps to its under evolution. However, in Massless QED, linearized gravity, quantum gravity, the corresponding Hilbert space contains a vacuum. Okay, so let me just kind of summarize. So in order to have an infrared finite scattering theory, one must include states with memory in a Hilbert space, which is one separable, contains a dense set of physical states, and finally maps to itself under scattering. In massive QED, there does exist a unique Hilbert space, which satisfies 1 through 3. However, this construction appears to be more of a fluke than a guiding principle. Indeed, it fails to yield a suitable Hilbert space of physically reasonable states in massless QED, linearized gravity, or in full quantum gravity. In this paper that we'll be putting out shortly, we also studied non-Faddeev Coolidge representations. So note, these are not guaranteed to satisfy 3 because there's no conservation law unless you stick to eigenstates of the charge at spatial infinity. However, you can just ask whether or not there exists representations that just separable and contain physically reasonable states. And we argued such a construction is highly constrained, and there's really no natural constraint of such a representation, which just satisfies 1 and 2. I can again talk more about that if anyone is interested. But let me just end with this final point, which is that we stress that the algebra and the algebraic states that I was showing you before are perfectly well defined. They simply do not assemble themselves into a suitable Hilbert space. They do so in QED, but again, that appears more of a fluke than a guiding principle. A preferred Hilbert space is a convenient but not an essential feature of a theory. And in our paper, and I can again talk about this more, but I'll end this talk soon. So we construct an algebraic scattering theory where in algebraic states, so in lists of correlation functions are mapped to out lists of correlation functions, bypassing the need of a preferred Hilbert space. So this defines the quantum theory, the scattering theory in all such theories, in infrared finite scattering theory, in all such theories in which a preferred Hilbert space is not suitable or not naturally posed. Okay, so with that, I'll take questions and leave up this summary slide.
Okay, thank you, Gautam. Before we proceed to the questions and answer sessions, let me ask everyone to turn on their microphones for a round of applause in retribution to your talk.